A very good morning, students. Welcome back to online session on data structures and algorithms course. In our previous session, we have concluded the binary search tree concept, and we have also started the AVL trees. Okay, so quickly we will get into this AVL trees and we'll see what are these. So, as we discussed, AVL trees they were introduced in the year 1962 by three gentlemen by name G.M. Adelson, Welsky, and E.M. Landis, and they are named. I mean, AVL trees they are named after these three gentlemen's name. Like A from Adelson, V from Welsky, and L from Landis. So AVL tree. So as we said, AVL tree, it is an height balanced tree, height balanced binary search tree, because whatever properties your binary search tree is having, so that is all the nodes in the right side subtree, they must be greater than to the root node, and all the nodes in the left subtree, they must be lesser than the root node. This property, if your binary tree is satisfying, then we call that binary tree as binary search tree. And if your binary search tree, along with possessing the binary tree property, it is also having this height balancing property, means we call such a tree as an AVL tree. So what do you mean by height balanced? Height balanced tree, it has to maintain the balance factor. So that balance factor, how we are calculating? Simply, okay, subtract the left side subtree from right side, height of left side subtree from height of right side subtree, or subtract the height of right side subtree from left side subtree. In either way, you will get the balance factor. So that balance factor, it should be either 0, 1, or -1, nothing other than that. Okay, nothing other than that. So a binary tree is said to be balanced if the difference between height of the left subtree and height of the right subtree of every node. So this condition, as your tree, it is a recursive definition. So whatever property we are adding to the particular tree, that property must be satisfied by all the nodes present inside your binary tree. Okay, all the nodes present inside your AVL tree. Okay, node should have, I mean, should lose this property. If any of the node is losing the property, then ultimately you will not call that complete tree as the AVL tree. So here, when you are calculating the balance factor, we must calculate the balance factor for all the nodes present inside your AVL tree. Okay, so in other words, we can say a binary tree is said to be balance factor if the height of the left subtree, left and right children of every node differ by either -1, 0, or +1. Okay, so a binary search tree, inside a binary search tree, if the height of every node, sorry, height at every node, whatever you are calculating, so if it is if you are subtracting the height of left side subtree from right side subtree, and if you are getting -1, 0, or 1, then we call such a tree as an AVL tree. So in an AVL tree, every node maintains an extra information known as balance factor. Okay, so we can define the AVL tree as an AVL tree is a balanced binary search tree. What is your AVL tree? It is a balanced binary search tree. In an AVL tree, balance factor of every node, it must be either 1, -1, or 0, nothing other than that. Okay, so what is balance factor? So balance factor, we said, it is the difference between the height of left subtree and right subtree. Okay, the difference between the height of left subtree and right subtree, we call it as a balance factor. The balance factor of a node is calculated simply by using that formulae only. So in either way you can calculate, either you subtract the height of left subtree from right subtree, or subtract the height of right subtree from left subtree. In both the ways you will get the uh, balance factor. So balance factor equals to, we have written the formulae over here. Balance factor equals to height of left subtree minus height of right subtree. In either way you can calculate, but we standardized like this and will go in this approach only always, because there should be some what we call standard. Okay, there should be some standard. I mean, in either way you can go, but when you have started calculating the balance factor with one formulae, use the same formulae for all the nodes present inside your binary, present inside your binary search tree. Not do like this. For one particular node you are using the first formulae, and for another node you are using the second formulae. Don't do like that. For all the nodes you have to use only one formulae. So to avoid that confusion, simply what we are saying, balance factor we must calculate using this last formula only, whatever I have given over here. Height of the left subtree minus height of the right subtree. Use this formula only for calculating the balance factor of all the nodes. Okay, so AVL tree I have given an example over here. As you can see, it is a binary search tree because root node it is 25, and whatever nodes we have inside the left subtree they are smaller than the root node, and whatever nodes we have inside the right subtree they are greater than the root node, isn't it? As you can see over here, see whatever nodes I have into the whatever nodes I have into the left subtree, over here, this one 20, 10, 22, 12, all they are smaller than the 25 root node, and whatever nodes we have inside the right subtree, all they are greater than the root node, that is 25. Okay, so if you maintain like this, it will become a binary search tree, and along with that, if you calculate the balance factor of all the nodes, so over here no left side subtree, no right subtree, so the balance factor will be 0. Okay, 0 minus 0, 0. Here here this direction we don't have any nodes, so the here height is 0 and here height is 1, so 0 minus 1, minus 1 we got. Likewise, we have calculated the balance factor of all the nodes and we got the balance factor either 0 or 1 or minus 1, nothing other than that we are seeing over here. So it is a AVL tree because balance factors it is satisfying, property of height balancing it is satisfying, so we call it as an AVL tree. So every AVL tree is a binary search tree, and not all binary search trees are AVL trees. So this statement we have concluded in our previous session only, and in today's session we will see a new concept, that is the AVL tree rotations. Okay, AVL tree rotations, and why we have to go for, I mean, what exactly this rotations concept and why we have to go for these rotations, all those things we will see in today's session. So it is very simple to understand. See, whenever, I mean, if you have a tree, we should have the flexibility of inserting the new node, we should have the flexibility of deleting the nodes, performing search, performing traversals, isn't it? So all these things we can do on a tree. So every tree we are doing these 4 types of operations: insertion, deletion, search, traversal. We discussed these 4 types of operations for your binary trees, binary search trees, and AVL trees also we will do the same thing. Okay, so whenever you are doing these operations, okay, in these 4 operations, search and traversal, they are very simple operations, because in search and in traversal we are not doing any modifications to the tree, isn't it? We are not removing any nodes, or we are not adding any nodes whenever we are performing either search or traversal. And believe me, this traversal technique, it is very similar to the traversal techniques whatever we performed in binary search tree. Your in-order, pre-order, post-order traversals, they are quite same. There is no difference. Whatever type of tree you will take, all types of trees, your binary trees, binary search trees, AVL trees, we do the traversal in the same way. We use that in-order, pre-order, post-order traversal techniques only. That is the reason why this question, it is very important, and many of the times they ask this question for 7 marks. And for this time, as they are framing LAQs for 15 marks, there is a possibility that they will give this type of question for 15 marks. See the weightage, how it is, I mean, increased. So if you simply take the concepts like binary tree, what exactly we do in that, what is the properties of binary tree, how we are doing the implementation, what sort of operations we are performing, what is the concept, prepare everything. That means you will get 15 marks. Again, come to binary search tree, what additions we are doing, because binary search trees we are creating on top of binary trees, isn't it? Binary search trees we are creating on top of binary trees, because whatever properties your binary trees will have, the same properties your binary search trees will also have, isn't it? Extra one property we are adding, that is all the nodes, they must be ordered nodes. Okay, lesser nodes, I mean smaller nodes in left subtree, greater nodes in right subtree, only that property we are satisfying, and that same property we are satisfying at every node, not only the root node but every node. And if your tree satisfies all these things, then we call the tree as binary search tree. And binary search tree we do the same thing: insertion, deletion, traversal, search. In these four operations, again, search and traversal, they won't affect the tree structure. But whereas insertion, deletion, they affect the tree structure. So in AVL tree also, the same thing will apply. In AVL tree also, we do the same four types of operations: insertion, deletion, traversal, search. And in among these four, traversal, search, they won't affect the structure of your AVL tree. But whereas the insertion and deletion, they affect the structure. And sometimes whenever you are performing these type of operations, insertion and deletion, the tree will also lose its balance factor property. The tree will also lose its height balancing property. So at that time, what we have to do means we have to go for this concept, rotations concept, and with rotations only we are going to get back the height balancing property. Remember this one. Whenever we are doing insertion or whenever we are doing deletion, okay, there is a possibility that the AVL tree will lose its height balancing property. So losing height balancing property means what? The balance factor will become other than -1, 0, 1. If you are getting the balance factor other than -1, 0, 1, that means your tree has lost its height balancing property. Your AVL tree has lost its height balancing property. So immediately what we have to do, we have to perform a suitable type of rotation. Okay, rotations, we have different types. A suitable type of rotation we perform and we get back the height balancing property. So quickly we read these three statements over here. Already I have explained those things. Again, we read. If anything we are missing, that we will, by reading we will come to know. So in an AVL tree, after performing operations like insertion and deletion, we need to check the balance factor of every node in the tree. Yes, after performing insertion, after performing deletion, you have to check the balance factor once again. If every node satisfies, I mean after insertion, after deletion, if every node satisfies the balance factor condition, that condition is all balance factors must be either 0 or 1 or -1, nothing other than that. So if every node of your AVL tree, even after performing insertion or deletion, it is satisfying the balance factor condition, we don't do anything because the tree structure has not modified. I mean the tree structure, it is satisfying the height balancing property. So we will not do anything. We will not do anything and we conclude the insertion or deletion operation there itself. We conclude the inserting of new node or deleting of the existing node there itself. Will not go beyond and will not do any rotations or stuff. Okay, so when we do the rotations means whenever the tree becomes imbalanced after performing insertion or deletion, if the tree becomes imbalanced. So what do you mean by imbalance? Imbalanced tree, you are getting the balance factor other than -1, 0, 1. So due to any of the operations what you have performed, then we have to perform rotation operations again to make the tree balanced. Again to make the tree balanced, what we have to do, we have to perform the rotation operations, and those rotation operations we will discuss over here in this particular slide. So rotation operations are used to make the tree balanced. Remember this one. Whenever the tree becomes imbalanced, we perform rotations to make the tree balanced. Okay, rotation is a process of moving nodes either in the left side direction or in the right side direction. What is rotation? In the process of rotation, we move the nodes either in the left side direction or in the right side directions. So we have four types of rotations, and these four types of rotations are classified into two different types. Okay, we have four rotations and they are classified into two types. So the first type, single rotation; the second type, double rotation. So as you can see over here, rotations, they have classified into two types. The first one, single rotation; the second type, double rotations. And in this single rotation we have two rotations, and in this double rotations also we have two rotations. So single rotation, we call it as left rotation, LL rotation, left rotation or LL rotation. So we call it as left rotation or LL rotation. Okay, LL rotation stands for left rotation, LL stands for left rotation. Then we have right rotation, RR rotation, left rotation, LL rotation, right rotation, RR rotation. Again, RR stands for right. RR stands for right rotation. Okay, instead of repeating the term right, we simply call it as right rotation or single right rotation. Sometimes we also call it as single right rotation or single left rotation because we perform the rotation only once. Okay, we perform the rotation, we perform the moving of nodes only once. So that is the reason why we call it as single rotation. Then we have double rotation. Okay, double rotations means we perform the rotation two times. Okay, two times. So this is these double rotations, they are two, left right rotation, right left rotation, left right rotation, right left rotation. Again the short form, if you see, LR rotation, RL rotation, LR rotation, RL rotation. Okay, so just we'll discuss all these four types one by one. So we'll start with left rotation or single left rotation or LL rotation. Okay, left rotation, single left rotation, LL rotation, left left rotation. So when we have to perform this left left rotation means, so suppose whenever you are doing the insertion operation and you are inserting a new node into the left side subtree of the left side subtree. Okay, okay, if you are inserting a new node into the left subtree of the left subtree, remember like this, sorry, not left subtree, right subtree of the right subtree, remember like this. Okay, how we are doing the insertion? Whenever you are doing the insertion operation into the right subtree of the right subtree, right subtree in the sense, if you have the root node, where is my cursor? Okay, here, if you have the root node and this is your right subtree, this is your right subtree, and you are inserting a new node as right subtree of the right subtree. So for root node, this is your right subtree, isn't it? This entire thing is right subtree, and you are inserting a new node as right subtree of the right subtree. Okay, this is root node. For this root node, this thing is right subtree. Okay, this thing is right subtree, and we are inserting a new node as right subtree of the right subtree, as right subtree of the right subtree. So whenever you are doing insertion in such a way, okay, right, right, whenever you are doing an insertion in that, in such a way, we go for opposite type of what we call rotation, opposite type of rotation. That is, as we did right right, we perform LL rotation. Remember this one, we perform LL rotation. So whenever you are inserting a right side, I mean a new node into the right subtree of the right subtree, right subtree of the right subtree, then we perform LL rotation. LL rotation, left left rotation. In left left rotation, what we do, we move every node one position in the left side direction. We move every node one position in the left side direction. To understand this more clearly, we'll go to the next slide, and here you can see. To understand LL rotation, let us consider the following insertion operation onto an AVL tree, into an AVL tree. So first what we are doing here, we have to insert 1, 2, 3 in the same order as they have written over here. In the same order as they have written over here. So first what I have to do, I have to insert 1. Insert 1. So after inserting 1, we have to after every insertion, we have to calculate the balance factor. So I have inserted 1, so now I have to calculate the balance factor. No left side subtree, no right side subtree. So 0 minus 0, balance factor 0. Now you try to insert 2. So after inserting 2, so first we were having 1. So let me just delete this one. Let me just delete this one and start again. Okay. After, yeah, 2, how I can see all insertion operations, whatever we are performing on an AVL tree, you have to follow the same procedure how we did in binary search trees. Okay, binary search trees, in that same way we do the insertion over here. So how we do the insertion in binary search tree? So whenever you want to perform the insertion of a new node, simply compare that new node with root node, isn't it? Compare that new node with root node. So 2 we have to compare with 1. 2 is greater, so we have to move in the right side direction, and right side direction it is null. So insert the 2 as the right child. Insert the 2 as the right child. So after inserting 2, calculate the balance factor, and always calculate the balance factors from the leaf nodes. Don't start from the root node. Always calculate the balance factors from the leaf nodes. So all these points you better write down in your running notes, because they will not be available. They won't be available inside your notes. Whatever concepts necessary, that only I have written. Okay, so here for this leaf node, the balance factor is 0, because no left child, no right child. So the balance factor is 0. But for this 1, left child is 0, but right child we have 1. So 0 minus 1. So it will become minus 1, like this. Okay. Still, the the tree is height balanced because balance factors are 0 or -1. Okay, still we are not losing the balance factor. Okay, not deviating the balance factor. So now you try to insert 3 as well. So inserting 3, what I have to do, 1 2 we already have, 1 2 we already have, so we have to insert 3. So start with root node, compare 3 with root node 1. So 3 is greater, so we move in the right side child. Okay, again come to this 2, make 2 as root, again compare this 3 with 2, 3 is greater, so insert the 3 as the right child of this 2. So like this. So after inserting 3, again you try to calculate the balance factors. So for this 3, we have to start from leaf node. For this 3, balance factor is 0. No left child, no right child. So balance factor is 0. For this 2, no left child, but right child 1 we have. So 0 minus 1. So the balance factor will become -1. Again, for this root node, when we are calculating, no left side subtree. So the height is 0. But right side subtree height is 2. So 0 minus 2, the height will become -2. So here the balance factor is -2. So the tree become unbalanced. The tree become unbalanced. So that statement I have written, tree is unbalanced, imbalanced. So -2, -1, 0, the tree is imbalanced. And why the tree became imbalanced in the sense, because we have inserted a new node into the right subtree as right subtree, isn't it? Into the right subtree as right subtree. Right insertion we have done, because of that the tree became imbalanced. So what we have to do, we have to perform left rotation. We have to perform left rotation. So in left rotation, what will happen means all nodes will move one position to the left side, one position to the left side. So this one will move over here, this 2 will come in 1's position, and this 3 will come in 2's position. See, as you can see over here, this 2 will move over here. This 1 will move over here, 2 will come in 1's position, and 3 will come in 2's position. So after performing rotation, right rotation, my tree will become like this. So 1 I moved over here like this, 2 I made it as root node like this, and 3 I shifted to 2's position, so like this. Okay, so now after LL rotation, tree is balanced now, because you calculate the balance factor here 0 0, isn't it? These two are leaf nodes, so 0 0. And when we are doing this balance factor calculation for root node, left subtree 1, right subtree 1, so 1 minus 1, it will become 0 only. So 0 0 0 we got. After performing the rotations, 0 0 0 we got. So now the tree is balanced. LL rotation we perform to make the tree balanced. So the next type of rotation is a single right rotation, or right rotation, or RR rotation we can call it as. So in RR rotation, what we do, exactly opposite thing we do. What we have done in left rotation, exactly opposite thing we do. So whenever you are inserting a new node into the left subtree as left subtree, into the left subtree as left subtree, AVL tree may become unbalanced if a new node is inserted into the left subtree of the left subtree. Then the tree then needs a right rotation. Okay, right rotation we have to perform, single right rotation or right rotation or RR rotation we have to perform. Okay, so in RR rotation, what we do, we move every node one position to the right from the current position. Okay, one position to the right from the current position. We have to move all the nodes, I mean whatever nodes, not all the nodes, whatever nodes are involved in that balance factor calculation. Because of that, see, first we have to note down the critical node. I forgot to mention that one. Critical node where exactly the balance is imbalanced, the balance factor is imbalanced. So over here, when we did the insertion, because of this because of this 3 insertion, whatever 3 we have inserted into the, where is my cursor? Yeah, here I have the cursor. Whatever 3 I have inserted over here, because of that I lost the balance factor over here. So wherever I lost the balance factor, I call that node as critical node. Okay, critical node. Because of that node only, my tree is become imbalanced. So I have to satisfy this thing. So from there only I have to start the rotation. From there only I have to start the rotation. So here also we do the same thing in right rotation, because we have inserted the new node in the left side subtree of the left side subtree. Because of that, the tree lost its balance factor. So immediately what we have to do, we have to find out the critical node, and from there only we perform the right rotation. So in that right rotation, how we do the insertion, you see. See, to understand the RR rotation, let us consider the following insertion operation. So first we have to insert 3, then 2, then 1. So do that quickly. So first what we are doing, inserting 3, calculating the balance factor, 0 minus 0, 0. So nothing changed. So then insert 2. 3, we are comparing 2 with this 3, it is smaller, we made 2 as left child. Okay, now calculate the balance factor. For 2, balance factor is 0, and for 3, balance factor is 1, because left side subtree height 1, right side subtree height 0. So 1 minus 0, it will become 1. So like this we got. Still the tree is AVL tree only, because we did not lose the balance factor. Then try to insert 1. How we can? 3, 2 we have. Okay, 3, 2 we have, and we are inserting 1. Compare that 1 with 3. How we do in binary search tree? The same way we do. Compare that 1 with 3. It is lesser. So move in the left side child. Compare that 1 with 2. Again lesser. So insert that 1 as the left side subchild of these 2. So now calculate the balance factor. For this 1, balance factor is 0. For this 2, 1 minus 0, 1. For this 3, 2 minus 0, it is 2. So here we are missing, I mean we are losing the balance factor, it is deviated. We got 2. So now we got this one. So again, we lost the balance factor at 3. So we made this 3 node as the critical node. So from here only we have to start the rotation procedure. And in what direction we have to move, I mean what type of rotation we have to perform. Because of the insertion of a right child into the right subtree, we got the we lost the tree became the imbalanced. The tree is imbalanced. So now we have to perform the right rotations. Okay, because of the insertion of a left child into the left subtree, we lost the property. So we have to perform right rotation. So this 3 will move over here, 2 will come to 3's position, 1 will come to 2's position. The same thing we did over here. And after rotating 3, it came like this over here. After moving 2 to 3's position, 2 will become the root node, and after moving 1 to the 2, and 1 will become the left child. So like this we got, and after calculating the balance factors, we got 0, 0, 0. So the tree is balanced now. The tree is balanced now. So the next type of rotation, it is a double rotation, and it is somewhat complex when compared with single rotations. Double rotations, they are slightly complex when compared with single rotations. So in double rotations, we perform a sequence of rotations, not a single rotation, a sequence of single rotations, like 2 single rotations we perform. As part of double rotations, 2 single rotations we perform. Okay, and they are the first type is the left right rotation. Left right rotation. So this is very simple. When we perform the left right rotation, in the sense, suppose if you are inserting a new node as yeah, inserting a node as inserting a node, not as, into, you write over here. Here is this one. Inserting a node, take the marker. This is very, very important statement. Inserting a node into left subtree as right subtree. This statement very, very important. As a right subtree. Inserting a node into left subtree as right subtree. If you are doing this, take L because L is coming first, left is coming first. So take L from here, R from here, R from here. Okay, LR rotation. LR rotation we need to perform. And in LR rotation, what we do? First we perform single left rotation. LR rotation, how we do? Single left rotation. Okay, then single right rotation. Single right rotation. 2 rotations we perform. Single left rotation, that means we have to move in this direction, like this. Then single right rotation, that means we have to move in this direction. So like this LR rotation we perform. So whenever we are inserting a new node into left subtree, that means Suppose if you have the root node and left node like this is your left node, isn't it? How, where we are inserting into the left node as right node. So like this, left node, right node. So here we need to perform left right rotation. If you're, I mean, doing so, if you are losing the balance factor, then only you have to perform the left right rotation. Otherwise, don't perform. If you're not losing the balance factor, don't perform. If you are losing the balance factor, then only you perform. Then only you perform. So quickly we go and see the example. First you read out all these three statements over here. Double rotations are slightly complex version of single rotations. The LR rotation is a sequence of single left rotation followed by a single right rotation. Already I have explained. In LR rotation, at first every node moves one position to the left and one position to the right from the current position. First we move the tree in left direction, then we move the tree in right direction. Okay, so quickly we go and we see the example. To understand the LR rotation, let us consider the following insertion operation inside an AVL tree. So how we are doing? First we are inserting 3. So the 3 insertion I am doing, and inserting 3 you will not lose the balance factor, you will get 0 only. Then try to insert 1. Compare 1 with this 3. Okay, compare 1 is this 3 with this 3. 1 is smaller, so it will become a left child. Okay, here the balance factor 0, here the balance factor 1. 1 minus 0, 1. Then try to insert 2. Compare that 3, 1 we already have. Okay, 3, 1 we already have. So to insert 2, compare the 2 with this 3. It is smaller, so move in the left child. Then compare the 2 with this 1. It is greater, so move in the right side. It is null, so insert the 2 as right. Like this. Now calculate the balance factor. Over here it is 0, over here it is 0 minus 1, it is minus 1, and over here it is 2 minus 0, it is 2 only. Because here the height is 2 and here the height is 0. So 2 minus 0, it is 2 only. So doing so, I mean inserting this new node, 2 node into the AVL tree, the AVL tree is losing its balance. Okay, it is a binary search tree, but it is not an AVL tree. Here we got the balance factor as 2. So now what we have to do? You have to make this imbalanced AVL tree as a balanced AVL tree. So for that we have to perform rotations. And what type of rotation we have to perform? Because we have inserted a new node into left subtree as right subtree. Left subtree as right subtree. So LR rotation we have to perform. First we move in the left direction. So when you are performing the first operation, don't consider the critical node. When you are performing the first operation, that is left rotation operation, don't consider the critical node. Rest of the nodes, whatever you have, perform the rotation on those 2 nodes only. So our critical node is 3. Our critical node I am highlighting over here, it is 3. See over here, the same tree structure here we have 3, 1, 0. 3, 1, 2. Balance factors 2, minus 1, 0. And here we are losing the balance factor, isn't it? Here the balance factor got deviated, so we made this 3 as our critical node. We made this 3 as our critical node. We make this 3 as our critical node. So now first type of rotation without critical node, and second type of rotation with critical node we perform. Remember this one. Whenever you are performing double rotations, first rotation you have to perform without the critical node, and second rotation you have to perform with critical node. Remember this one. So now, as we lost the balance factor, the first type of rotation, because we said LR rotation we have to perform. So first rotation is left rotation and then right rotation. So left rotation we have to perform without critical node, and RR rotation we have to perform with critical node. So in this entire balance tree, I mean in this entire subtree we have to perform the rotations. So first what we have to do, without critical node we have to perform. So we have to move this 1 in this direction because we have to perform left. Then 2 in this direction like this. So after moving like that, see, 1 we are moving over here, 2 we are moving over here. After moving like that, 1 will come down and 2 will become the root of 1, because 2 in this position we are moving, 2 in this position we are moving, and 1 we are taking down like this. Okay, so 1, 2, 3 like this you will get. 1, 2, 3 like this you will get. Again you calculate the balance factors here, 0, 1, 2 only. Okay, 0, 1, 2 only. Still we have to perform one more rotation, and it is a single RR rotation we have to perform. Okay, RR rotation. Left rotation already we performed. Now we are performing right rotation. So after performing right rotation, 3 will go down, 2 will come in 3's position, and 1 will come in 2's position. 1 will come in 2's position. So the same thing we are doing. 3 we are shifting down, 2 we are bringing to 3's position, and 1 we are bringing to 2's position. So we got like this. So after making like this, when you calculate the balance factors 0 0 0, the tree is balanced. So the next type of rotation, the last type of rotation technique, it is the right left rotation. Right left rotation, when we have to perform, means whenever you are inserting a new node, inserting a new node into the right subtree, into the right subtree as left subtree, as left subtree. If you are doing like this statement, I have to include over here. Actually, I forgot to mention this point here also, and here also one extra point I forgot to mention. I will mention that one, no issues. Inserting a new node into the right subtree as left subtree. Whenever you are doing like this, and because of this insertion, if your tree is losing the balance factor, then immediately you have to perform what type of rotation? First you are writing right, so R from this right, and then you are writing left, so L from this left. So RL rotation you have to perform. That is right left rotation you have to perform. And it is a combination of two rotations. Right rotation, right rotation, and left rotation. Left rotation. Right rotation, left rotation. Okay, RL rotation means we have to perform two single rotations. First single rotation is right rotation, and second single rotation is left rotation. It is a combination of two. Okay, so again, when you are performing right rotation, the first type of rotation, don't consider the critical node. Ignore the critical node and perform the right rotation. Then when you are performing the second left rotation, then consider the critical node and perform the left rotation. Simply to understand this, we'll move to the next slide and we'll see what insertions we are doing. First we have to insert 1, then 3, then 2. So first insert 1. So 1 we are inserting, and balance factor is 0 because no left, no right. Then insert 3. So 1, compare the 3 with 1, it is greater. So insert the 3 as right child. Okay, insert the 3 as right child because right is empty over here, null over here. So again, balance factor here 0, here 0 minus 1, minus 1. Again, we do the insertion of 2. We have 1, 3 already inserted. Now we are doing 2 insertion. So compare the 2 with 1, it is greater. So move in the right child. Okay, compare the 2 with this 3, it is smaller. So make the 2 as left child over here. Like this, calculate the balance factor. Over here the balance is 0 because no left child, no right child. Over here the balance factor is 1 minus 0, this is 1. And over here the balance factor is 0 minus 2, it is minus 2. So here we lost the balance factor, we got minus 2. So again, quickly see this tree, AVL tree. It is no more an AVL tree because here we have the balance factor minus 2. It is no more an AVL tree, and this is where we are losing the balance factor over here. At this particular node we are losing the balance factor. So this is your critical node. So what we have to do, I mean, how we got this imbalance in my AVL tree? Because I have inserted a new node into right subtree as left. Okay, right left. See here, right left. So RL I have to perform. Right left rotation I have to perform. So first I have, when we are performing right, don't consider the critical node. Simply move this 3 here, move this 2 here. The same thing we are doing over here. Moving 3 down and bringing 2 up. Moving 3 down, bringing 2 up. So after that what will happen? See, 2 will come in 3's position and 3 will come down. So 2 will come in the middle and 3 will come down. So again you calculate the balance factor. So here the balance factor of 3 is 0, balance factor of 2 0 minus 1 minus 1, the balance factor of 1 0 minus 2 minus 2. So still what we have to do, still the tree is not imbalanced. Again, initially only we decided that we have to perform RL rotation, so we performed only R. Now we are performing L. L, how we have to perform? By considering the root node. I mean, that is critical node as well. So critical node also we considered, and all the nodes we are moving in the left side direction because we are performing left rotation. So 1 will come down, 2 will go in 1's position, 3 will go in 2's position. So like this you got. And after getting this one, again you calculate the balance factors, and all the balance factors, they are zeros, so the tree is balanced now. So in this way we perform the um, what we call rotations inside your AVL tree. So quickly we construct an AVL tree by using these simple node elements. Okay, so whatever node elements we have over here, like 63, 9, 19, 17, 27, sorry, 19, 27, then 18, 108, 99 and 81. By using all these nodes, we perform the we construct the AVL tree. Okay, it is very simple operation. Step by step we move, and step by step we see how we can perform the insertion operation on an AVL tree. I mean, after inserting first node, ultimately we are doing the insertion of second node. That is nothing but insertion of what we call, let me just give some time. Okay, we start with our first node, that is 63. Okay, our first node, which is 63, we have to do the insertion of that 63. So simply make that 63, because before inserting that 63, our AVL tree is empty. So make that 63 as the root node. Okay, so we are doing that thing over here. I'm making the 63 as a root node. Okay, so after inserting 63, select 9. So we said in the same way how we do the insertion in binary tree. So after inserting 63, calculate the balance factor, that is 0, no left, no right. So balance factor 0. Then try to insert 9. Compare 9 with this 63. It is smaller. So 63, make this 9 as left child. Okay, left child. Again calculate balance factor. For 9, 0. For 63, 1 minus 0, it is 1, like this. So no, we did not lose any balance factor over here. So now go to 19 and try to insert 19. Try to insert 19. So what we have to do, compare this 19 with 60. Yeah, 63 I'm drawing, then 9 I'm drawing. Now 19 we have to, 19 we are comparing with 63, it is smaller, so move in left side direction. Okay, 19 compare with this 9, it is greater, move in right side direction. So that 19 will come over here, 19 will come over here. Now how we, I mean, now calculate the balance factors. So here for 19 the balance factor is 0, no left, no right. For 9 balance factor minus 1, 0 minus 1 minus 1. For 63 balance factor 2 minus what is 0, 2 minus 0, it is 2. So here we lost the balance factor, isn't it? We lost the balance factor. So what we have to do, we have to perform the rotation. What type of rotation we have to perform? Because of inserting this 19, I've lost the balance factor. So that 19, how it got inserted, and this is my critical node. This is my critical node. Okay, how I lost the, I mean, how I lost the balance factor? Because of inserting this 19. So 19, how it got inserted to this critical node? Inside the, only we have to check to the critical node, don't check the entire tree. Only we have to check with the critical node. So for this critical node, we have inserted 19 as left subtree, into the left subtree as right subtree, left, right. Okay, so LR rotation I have to perform. What type of rotation? LR rotation I have to perform. that LR rotation after, yeah, it is a combination of two. When you are performing left rotation, don't consider the critical node. And when you are performing the right rotation, consider the critical node. So first I have to move in this way. 9 will come over here, 19 will go up. In this way I have to move. So see, 63, then we are saying 19, then we are saying 9. So like this. So now again you calculate the balance factors. This is 0, this is minus 1, no, this is 1, this is 2. Okay, 1 minus 0, 1, 2 minus 0, 2. So like this. Still the tree is not balanced because still one more operation, I mean one more rotation is pending, that is right rotation is pending. So when you are performing right rotation, you have to consider the critical node as well. So critical node will come down, 19 will go up, 9 will also go up. So after making like that, 19 will become the root node, 63 will come down, 63 will come over here, and then 9 will come over here. See, now you calculate the balance factor. For this it is 0, for this 1 minus 1 it is 0, for this 63 again there is no left no right, so it is 0 only. So like this, now the tree is balanced. Immediately whenever the tree is becoming imbalanced, immediately you have to take the necessary action. So likewise, so the same thing, yeah, after that we have to insert 27, right? So I will take this entire thing to the whiteboard. Okay, I will take this entire thing to the whiteboard. So what we have over there, we have 19, 9, 63. We have 19, then 9 here, 63, and balance factors 0, 0, 0. Still what else we have to insert? That all numbers I'm writing over here. Control Z, Control Z. 63 we have, then 9 we have, 19 we have, after that 27, 18, 27 we have, 18 we have, 108, 99, 108 we have, 99 we have, then 81. See, listen this very carefully because I will give an assignment on this one. So 63, 9, 19 we have already inserted. So we are going for 27 now. 27 compare with root node, it is greater. So come over here with 63. Okay, come to 63. Compare with this 63, it is smaller. So 27 will come like this, 27. So after doing like this, again you calculate the balance factors. Remove this. Okay, remove this as well, and remove this as well. Now you calculate the balance factors. For this 27 it is 0. Okay, for this 63, 1 minus 0, 1. For this 9 it is 0. Okay, for this 19, 1 minus 2, isn't it? 1 minus 2, so it is minus 1. So nothing, I mean all balance factors are either zeros, ones, or minus 1. No balance factor lost. So again what we have to do, we have to insert 18 into the AVL tree. So again start comparing this 18 from the root node, 19 with 18, it is smaller, so move in this direction, compare 18 with 9. Okay, it is greater, so insert that 18 as the right child over here. So suppose simply 19 will come over here, 9 will go over here. Okay, then we have like this 63 here, sorry, 63 over here, then we have 27 like this. Okay, then we are, I mean, inserting 18, so comparing 19, it is smaller, we are moving in this direction, comparing with 9, it is greater, so right side, so like this it will come. After inserting 18, quickly calculate the balance factors. For 18, 0, for 9, minus 1, because 0 minus 1, it is minus 1. For 27 it is 0. For 63, 1 minus 0, it is 1. For 19 now, for 19 here also 2, here also 2. So 0, 2 minus 2, it is 0. So nothing lost. Still the tree is balanced. So next we have to insert 108. We have to insert 108. How we can? Compare with this 19, 108, greater. Compare with this 63, 108, greater. So that 108 will come over here. 108, like this it will come. So remove the balance factors and calculate the new ones. Only this thing will change and this thing will change. Here it is same, here it is same. Okay, okay, 0 for this, 0 for this, 0 minus 1 only. For this 0. For this also 108 also 0. For 63 1 minus 1 it is 0. For 19 here 2 minus 2. Again it is 0 only. Again it is 0 only. So nothing has changed. Nothing has changed. So now you go and insert another node, that is 99. You insert 99, you try to insert 99. How we can compare with 19? 99 compare with 19, it is greater, move in this direction. Compare with 63, 99 compare with 63, again it is greater, move in this direction. 99 compare with 108, it is smaller. So insert that 99 as the child node, right, left child node for this 108. So now this will change, this will also change. I guess this will also change. Quickly we see. Yeah, for this it is 0 only, balance factor. For this 1, for this 0 only. For this 1 minus 2, isn't it? 1 minus 2, so minus 1. For 63 it is minus 1. So then for 19, this is 2 and this is 3. 2 minus 3. 2 minus 3, it is minus 1. See, again the tree is balanced because all my balance factors are either zeros, ones or minus ones, nothing other than that. So the tree is balanced. Now try to insert this last node, whether it is 8 or 81. 81, the last node is 81. So we have to insert 81. Compare 81 with 19, it is greater. Come to 63. Compare 81 with 63, it is greater. Come to 108. Compare 81 with 108, it is smaller. Go to 99. Compare 81 with 99, it is smaller. So insert that 81 over here as the left child of this 99. Okay. So now what things will affect here? This thing, basically this thing will also affect, and this thing will also affect. We'll see quickly. So for 81 it is 0, balance factor, no left no right, so 0. For this 99 it is 1. Okay, 1 minus 0, it is 1. For this 108, 2 minus 0, it is 2. Okay, 108, it is 2. Again for here also what it is? 0 minus 2, so this is minus 2. Here also what it is? uh, Here this is 2 and here this is 4. 1 2 3 4. Here it is 2, here it is 4. Height of left subtree, it is 2. Height of right subtree, it is 4. So 2 minus 4, it is minus 2. See, when you are losing the balance factor like this, so first balance factor where you lost, that is the reason why I told you to start from the leaf nodes, calculating the balance factor from the leaf node. Don't start from the root node. So when you have started the calculation of balance factor from the leaf nodes, which node lost its balance factor first, you make that node as critical node. So in our consideration, 108 lost its balance factor first, isn't it? 108 lost its balance factor first. So make 108 as critical node. 108 as critical node. So after this, what we have to do? What type of rotation we have to perform? Because why 108 lost its property balance factor? Because we have inserted a new node into the left subtree as left subtree. Left subtree as left subtree. Left. So whenever you have like that, you have to perform the opposite type of rotation, that is RR rotation. Whenever you are performing single rotation, you have to perform the opposite rotation, that is RR rotation. So RR rotation, what it tells? It tells you to move all the nodes, including the critical node, all the nodes one position in the towards right. One position towards right we have to move. As we have inserted the new node as left into the left subtree as the left subtree, we have to move all the nodes including the root node in right side position. So we have to move 108 should come over here, 99 should go in 108 positions, 81 should go in 99's position. So what will happen after the after the insertion, I will show you over here. After that addition, after that modification, after that rotation, yeah, what will happen, I will show you over here. So 19 will become the root node. Okay, then we got 9, then we got 18 over here, then we have 63 like this, then we have 27 over here. Okay, here we are moving. Here what will happen for this thing? 99 will go over here, 99 will come like this, and 108 will come as the right child, and this 81 will come over here, 81 like this. Start calculating the balance factors. This is 0, this is 0 minus 1 minus 1, this is 0, This is 0, this is also 0. So 0 minus 0, this is also 0. 0 minus 2, isn't it? 1 minus 2, sorry, not 0. 1 minus 2. 1 minus 2, it is minus 1. And here 2 minus 3, so minus 1. The tree is balanced now. The tree is balanced now, and it is an AVL tree. It is an AVL tree. Like this, you can perform the construct the AVL tree. The same thing I have shown over here. See, first we have inserted 63, then 9, then 19. After inserting 19, we are losing the balance factor at 63. So we perform two types of rotations. That is, first we perform the left rotation, left rotation, then we perform the right rotation, and after performing LR rotation, we got the tree balanced. Then we inserted 27, no loss, 18, no loss. uh, After inserting 108, no loss. Then we inserted 81. So when we inserted 99, we inserted no loss. Then 81 we inserted. So when we inserted 81, again we lost the balance. So we performed left rotation, single rotation, left rotation. So after performing LL rotation, again everything got balanced. Okay. Hopefully you understood this complete phenomenon, how I have shown over here. See here, the same thing we got here. Okay. 19 as the root node, 963 child nodes, 18, 27, 99, then 81, 108. Like this, we got the tree. Okay, I will give one example. In the assignment, you have to perform the same operation. You have to perform on a paper, step by step. You have to perform how I am doing over here. See how I am doing. I've started with one single node, then step 2, step 3, step 4. How I am proceeding, step 5. In step 3, I got um, um, imbalanced AVL tree, so I performed rotation. In step 4, I got the balanced tree. So like that same way you have to do. From step 3 to step 4, I have performed LR rotation. Then step 5, step 6, step 7, step 8, step 9. From step 9 to step 10, again we performed LL rotation. Likewise, you have to. So as we said, yeah, on an AVL tree, we perform the following operations, that is search operation, insertion operation, traversal operation, and deletion operation. And among these four, the search and traversal operation, they are same like your BSTs. They are same like your BST. How we do in BST, the same way we do in AVL as well, binary search tree. Okay, but the insertion, it is quite different, and deletion, it is quite different. That we will see in detail. So search operation, the search operation in AVL tree is same as what we have seen in binary search tree. Refer the search function of binary search tree. The same function, the coding, the implementation, the concept, same thing we follow in AVL tree case also. Then we have insertion. See, insertion, whenever we are doing insertion, every time we have to calculate the balance factor. If the balance factor is, within the limit, if the balance factor is satisfying the property, or if the balance factor is satisfying the balancing of the tree, then don't do anything. If at all your balance factor is not satisfying the rule, not satisfying the balancing property, then we have to perform any one type of rotation, either single rotation or double rotation. Okay. So this thing you have to remember. And we said the insertion operation on an AVL tree, it can be performed in order of log n time complexity, order of log n time complexity. So always a new node into your AVL tree, it gets inserted as the leaf node only. That thing also you have to remember. Okay. Then traversal, again it is also same like your BST, so we have to refer the traversal function in your BST. Deletion, same thing. Whenever you are deleting a node, if the tree is not losing the deletion operation, it is quite same like your binary search tree. So deleting three cases: deleting the leaf node, deleting a node with one child, deleting a node with two children. The same concept we have to perform. After applying that same concept, again you calculate the balance factors. And if balance factors are satisfying, then don't do anything. If the balance factors are not satisfying, then rotations. Phenomenon, concept, everything, it should stick into your mind. So deletion, how we are performing, the same way how we did in binary search tree, in that way only we are performing. Deleting a single node, deleting the leaf node, deleting a node with one child, deleting a node with two children. Three cases we have to follow. And after applying the delete operation, if your tree is losing the balance factor, apply the rotations to make the balancing. And if the tree is not losing the balancing, don't apply rotations. That's it. Simple concept. So in tomorrow's class, we will see the complete implementation of your AVL tree, including search, traversal, insertion, deletion. Everything we see in tomorrow's class. Hopefully you understood the concepts in today's stuff. Thank you very much, students.